Training and running generative AI models requires massive compute power, and as data privacy concerns and cloud costs rise, more teams are pushing to run those workloads locally. For local AI compute, NVIDIA's Ada Lovelace architecture is currently the standard, but deciding to use Ada Lovelace is the easy part. The lineup features over 14 distinct GPUs. Choosing the one that actually matches your specific workload usually leaves buyers paralyzed. That paralysis is compounded by a strict architectural constraint. Across the entire Ada Lovelace generation, NVIDIA completely removed NVLink. Without NVLink, you can no longer pool video memory across multiple GPUs with hardware-level efficiency. Each card now effectively operates in complete isolation. Because you cannot rely on multi-GPU memory pooling, your upfront choice of a single card dictates the absolute ceiling of the models you can train and run. Before filtering the hard way, we must look at the unified tech driving this entire generation. The main upgrade, across the board, is the 4th generation Tensor Core. By utilizing the new FP8 precision format, Ada's Tensor Cores process double the data volume of the previous Ampere generation, reaching 1.3 petaflops. That raw speed feeds into a specialized tool called the Hopper Transformer Engine. This engine is explicitly designed to optimize the massive matrix multiplications required to train and run large transformer-based models, like GPT-4. These architectural benefits are baked into the silicon, but NVIDIA distributes them across 3 wildly different deployment categories: data center, workstation, and consumer. To actually unlock all of that raw processing speed, you have to match the correct category to your physical environment and your budget. This matrix maps the entire lineup. We start with the data center tier, engineered for enterprise server integration. The flagship L40 and L40S, though, over 48 gigabytes of memory and 18,000 CUDA cores. But there's a rigid trade-off. They rely entirely on passive cooling. Without internal fans, they require specialized server racks that blast high-velocity air across the heatsinks to prevent overheating. For environments where power efficiency matters most, the L4 variant drops the power draw to a mere 72 watts. However, the L4 caps out at 24 gigabytes of memory. This makes it highly efficient for running AI inference, but insufficient if you are trying to train a massive language model from scratch. Data center GPUs offer 24/7 reliability for enterprise loads, but without a dedicated, climate-controlled server room, they are essentially highly expensive paperweights. Data scientists working outside a server room need the workstation tier. The top-end RTX 6000 Ada generation matches enterprise cards, offering 48 gigabytes of memory and 18,000 CUDA cores. The key difference is the cooling system. It features active cooling with a built-in fan. That means you can plug it directly into a standard desktop tower and access server-tier model training capabilities right at your desk. Shrinking data center power into a desktop format carries a steep price premium. You can drop down to the entry-level RTX 2020 Ada for a fraction of the cost. But this restricts your memory to 16 gigabytes, placing a hard cap on model size. Workstation GPUs solve the environmental constraints for solo professionals, assuming you have the enterprise-level budget to buy the top-tier cards. That leaves the consumer GeForce tier, the starting point for developers and hobbyists. The flagship RTX 4090 offers desktop-leading compute power with 16,000 CUDA cores and 24 gigabytes of VRAM, but it demands an extreme footprint, pulling 450 watts with a massive active cooling system. Because of that bulk and heat output, you cannot densely stack 4090 side by side. They will physically choke each other out. Moving down the stack, the budget floor is the RTX 4060 Ti. To hit a lower price, NVIDIA restricted the memory bandwidth to 288 gigabytes per second. You accept slower data transfers and longer training times just to secure the 16 gigabytes of memory required to load modern generative models. Consumer cards offer incredible raw value. However, their massive power draw, huge physical size, and strict 24 gigabyte memory ceiling prevent scaling to enterprise workloads. To narrow 14 GPUs down to 1, we can build a decision tree. This flowchart starts with a simple physical filter. Are you installing this in a server rack or a standard desktop? If you have a server rack, you choose based on workload. Heavy model training requires the L40S. Running efficient, continuous inference on existing models points to the L4. If you are using a standard desktop, you must filter by budget and memory requirements. Professional users requiring 48 gigabytes of memory need the Workstation RTX 6000. Consumer budgets capped at 24 or 16 gigabytes land on the GeForce 4090 or 4060 Ti. Notice how your physical environment and cooling setup effectively eliminate 2/3 of the hardware options before you even look at the compute speeds. So here is the baseline. If you run an enterprise lab, do not try to hack giant consumer cards into your server racks. Invest in the data center tier for stable, scalable density. If you are a solo data scientist needing massive memory, the Workstation tier is your viable path to 48 gigabytes outside of a server room. If you are a beginner or startup on a strict budget, the RTX 4060 Ti 16 gigabyte model is your critical entry point. It prioritizes the minimum required memory capacity over raw speed. Keep in mind, because NVIDIA removed NVIDIA Link from this generation, you cannot easily upgrade your total memory pool later by just plugging in a second card. Succeeding in AI hardware right now isn't about buying the highest core count. It comes down to predicting the maximum size of the models you intend to run and purchasing the single GPU that can actually fit them.